Welcome back to the channel. This is the second video in my project to animate a tilt rotor. In today's video, I'll cover the Pylon conversion system and the drive system, and I'll animate normal and engine failure operation of the drive system to show how power is transferred to both prop rotors when one engine fails. This video has chapters if you'd like to jump ahead to certain topics. So I haven't modeled the flight controls yet. That's a future effort, but I expect the animation of the flight controls to be some of the more interesting content of this series. Tilt rotors use indirect flight controls in a way that showcases some unique and interesting technology. If you like this content, please like, subscribe, and comment. And please consider buying me a coffee on buymeacoffee.com. That link is in the description. I'll start with a brief overview of tilt rotors in general. The model on the screen is a generic tilt rotor. It's not meant to represent any one specific design. I used technical data from the XV15 and the XV3 from a NASA report, and also some Wikipedia facts and figures for the AW609 and the MV22 Osprey. All the references are in the video description. A tilt rotor is a type of thrust vectoring aircraft that can hover for takeoff and landing, and then fly fast at speeds nearing 300 knots. A tilt rotor hovers by pointing the thrust vector upward. This is called thrust-borne flight, where the downwash created by the rotors generates the thrust needed to hover. Tilt rotors transition to forward flight by tilting the thrust vector forward. Generally, this is in one continuous motion, and during this transition, they also increase the wing's angle of attack as the aircraft accelerates. As the thrust vector tilts forward, less lift is borne by the rotor system and more lift is borne by the wing, until the thrust vector is in line with the chord of the wing. In this position, the tilt rotor is fully wing-borne. The process of transitioning from thrust-borne to wing-borne flight takes about 15 seconds. It takes slightly longer to convert the other direction. Deceleration from approach speed to a hover might take maybe a minute or so, depending on how aggressively the pilot maneuvers. Tilt rotors use airplane-style flight controls, such as ailerons, elevators, and rudders, but they also use rotorcraft-style controls, such as a swash plate and pitch control rods. And most modern tilt rotors use fly-by-wire flight controls, and this is necessary due to the complexity of the mixing that takes place between rotor controls in thrust-borne flight and lifting surface controls in wing-borne flight. A core safety feature of tilt rotors is the ability to fly with one engine inoperative. This is possible because of the wing interconnect drive shaft and the freewheeling clutches in the drive system. Another key safety feature is the ability to auto-rotate. For years during the development of the V22 Osprey, there were opponents of tilt rotor technology who doubted the ability to convert through the edgewise flow region of unpowered flight. But this capability was demonstrated in April of 2014 by the Augusta-Westland 609 team. This test dispelled the myth that there was a barrier to safe auto-rotation of tilt rotors. Let's talk about these systems and components. The Pylon conversion system uses a two-stage recirculating ball screw. My animation is very simple. I only show the helical raceways on the screws. I don't show the recirculating ball mechanism that creates the linear actuation. This would be inside the actuator, so you wouldn't see this even on a real tilt rotor without some disassembly. I added 3 redundant hydraulic actuators to the animation, although different tilt rotors in history have used different means of actuation. Some have used electric actuators, and some achieve redundancy via a mechanical cross-shaft. There's no safety effect if the Pylon conversion system fails while in thrust-borne flight. The pilots would just land and give the aircraft back to maintenance. But if failure in wing-borne flight is at least hazardous, possibly catastrophic, the rotors are going to be below the level of the landing gear. And because the Pylon conversion actuation system is safety critical, it's built with these multiple levels of redundancy. The drive system has several functions. It transfers power from 2 turbine engines to the prop rotors, reduces the speed from 30,000 RPM at the engine to 506 RPM at the prop rotors, provides for proprotor counter rotation and synchronization, allows one engine operating capability by transferring power from the good engine side equally to both proprotors, allows auto-rotation capability by declutching a failed engine from the rotor system, and finally it extracts power from the rotor system to provide hydraulic and electric service for the aircraft. These subsystems within the drive system provide those functions I just listed. There is a Proprotor Gearbox on each side of the aircraft. These transfer power from the on-side engine to its proprotor. There's also a tilt-axis gearbox on each side of the aircraft. These take power from the Proprotor gearboxes and pass it through the wing interconnect drive shaft in order to synchronize the left and right prop rotors during one engine in operative flight. A Pylon drive shaft connects the tilt-axis gearbox to the Proprotor gearbox. There's a Midwing Gearbox at the center of the interconnect drive shaft. The Midwing Gearbox extracts power from the drive system for hydraulic pumps and electric generators. And the final parts in the drive system are the rotor masts and the rotors themselves. That's an overview of the drive system. Let's take a look at the details. The Proprotor Gearbox provides a 3-stage 59-to-1 gear reduction. And there are 4 sections within this gearbox: the input gears, the clutch, the bull gear, and the planetary gear. The 3 reduction stages happen at the interface between each of those sections. One of the first challenges in designing a tilt rotor is to find a way to accommodate counter-rotating prop rotors. We'd like to use the same engine on both sides of the aircraft, so we'll need to reverse the direction of one of the prop rotors. In this case, both engines turn clockwise, but the left-hand prop rotor rotates counterclockwise, which is opposite the right-hand prop rotor. To solve this, we can add an extra gear to only the left-hand side. In this split-screen view, you see the power input on each side turning clockwise, but this extra gear on the left side results in counter-rotation of the 2 prop rotors. And by the way, if you're a tilt rotor pilot and you notice that your left-hand prop rotor gearbox temperature is always just a little bit warmer than the right-hand side, that's because of this extra gear in the left-hand gearbox. It results in slightly warmer oil temperature on that side. The first stage of gear reduction happens between the input pinion and the clutch input gear. The input pinion has 31 teeth and the clutch input gear has 137 teeth. The gear reduction math is on the screen, and this results in a rotation speed at the clutch input of 6,788 RPM. Interestingly, the number of teeth on that extra left-hand gear don't alter the gearing. The idle gear tooth count appears in both the numerator and the denominator, so it cancels out inside the equation. Because it doesn't change the RPM, it's called an idle gear. We'll cover the function of the clutch in detail in the engine failure chapter of this video. For now, I'll just make the brief point that when in powered flight, the input and the output side of the clutch turn in the same direction and at the same speed. In powered flight, the clutch passes power without slipping from the input to the output. And in this design, both ends of the clutch turn at 6,788 RPM. The second stage gear reduction happens between the clutch output gear and the bull gear. The clutch output has 37 teeth and the bull gear has 137 teeth. The gear reduction math is on the screen. The bull gear is reduced in speed to 1,833 RPM. The input to the planetary gear is called the sun gear, and this turns at the same RPM as the bull gear. The final gear reduction happens within the planetary by extracting power from the orbit rotation speed of the planet gears. To get this power out of the planetary, we have to add a planet carrier. The rotor mast is then splined to this carrier. And because the mast is in line with the shaft from the bull gear and the sun gear, they may look like they're connected, but they're not. The mast is connected to the planet carrier, and it turns at a slower RPM than the bull gear. The gear reduction math of a planetary is just a little more complicated than a simple ratio. That formula is on the screen if you're interested. and this results in a final rotation speed of the main rotors of 506 RPM. The tilt-axis gearbox is located behind the Proprotor gearbox, and its purpose is to transfer power from one side to the other during one engine in operative flight. There is a spiral bevel gear pair in the tilt-axis gearbox. The inboard gear in this pair is in the plane of conversion, and this allows the gear to simultaneously rotate on its own shaft axis and on the aircraft conversion axis during pylon conversion. This gear pair uses a 96-degree shaft angle to accommodate wing sweep. This results in the thrust axis being aligned with the forward flight direction when in wing-borne flight. But that gear shaft angle also results in the thrust axis being towed out a few degrees in thrust-borne flight. That exact angle is 2.5 degrees, which is the difference between the wing sweep angle of 6 degrees and the dihedral angle of 3.5 degrees. This outward tow-out is a necessity of geometry and isn't intentionally designed in for any aerodynamic reason. In fact, this tow-out causes a slight decrease in hover efficiency because the tip path plane is not parallel to the horizon. The means to transfer power across the wing of the aircraft following an engine failure relies on a pylon drive shaft that connects the tilt-axis gearbox to the Proprotor gearbox. And like the pylon drive shaft, the wing interconnect drive shaft also transfers power during an engine failure from the side with the good engine to the side with the failed engine. That drive shaft also provides mechanical synchronization of the prop rotors. Although, unlike aircraft like the CH-46, tilt rotor blades don't intermesh, so mechanical synchronization isn't critical for safety. In fact, as standalone failures, neither an engine failure nor an interconnect failure are catastrophic. In the presence of either one of those failures, power is still sent to both rotor systems. It's only the combination of those two failures that result in uncontrollable asymmetric thrust. In this top view of the interconnect drive system, you see that it's not a continuous shaft angle from the tilt-axis gearbox to the midwing gearbox. Instead, each of these flexible diaphragm couplings take up a small portion of that angular misalignment. Each of the couplings is capable of 3.5 degrees of direction change. In my design, each coupling takes up 1.6 degrees of misalignment, although real tilt rotors use more of these couplings, so each one would deform even less than what I show in the animation. The midwing gearbox is used to extract power from the drive system for hydraulic and electrical service. Earlier I had said that tilt rotors are capable of all-engine-out autorotation, but they're still fly-by-wire with hydraulically boosted flight controls. And like many large aircraft, they would be uncontrollable without hydraulic and electric service. This is why it's necessary to extract power from the drive system to power the flight controls. And unlike most transport airplanes, most tilt rotors do not use engine accessory drive for hydraulics and electrics. Instead, these are usually powered from the rotor drive system. Other airplanes use things like ram air turbines and auxiliary power units to provide this power during all-engine-out flight. But this isn't necessary in tilt rotors because the rotor drive system always rotates. It's always capable of powering those subsystems. I've mentioned engine failures a few times in this video and how the interconnect drive system is critical for transferring power after an engine failure. Another critical component when it comes to operating with a failed engine is the clutch within the Proprotor gearbox. This device is alternately called a freewheeling unit, a Sprag clutch, or an overrunning clutch. Those terms all mean the same thing. The purpose of the clutch is to allow a one-to-one transfer of engine power into the prop rotors, but to also automatically disengage after an engine failure when the power flows in the opposite direction. This device is functionally equivalent to the overrunning clutch found in most bicycles. With a bicycle, you want the ability to send drive power to the wheels when you pedal, but you don't want the wheels to power your legs when you're coasting downhill. We'll look at the internal mechanism that allows that to happen in a moment, but first let's take a macro look at what happens during an engine failure. What you see on the screen is the normal engine operating conditions. All of the gears in the Proprotor gearbox rotate, as does the engine gas generator spool and the power turbine spool. I'll now fail the engine, and a quick note on the animation. Normally when the engine fails, the clutch would immediately disengage, maybe within a few milliseconds. For instructional purposes, I'm showing a lengthened version of that moment in time after the engine failure, but before the clutch disengagement. Here the gas generator has stopped rotating, but all of the Proprotor Gearbox gears and the engine power turbine continue to rotate. The power turbine rotates because it's mechanically connected to the Proprotor Gearbox input gear. It's being backdriven by aerodynamic forces through the rotor system, and the things I've identified with callouts continue to rotate at very high RPM and extract a large amount of parasite power from the gearbox. Because the RPM is so high, the amount of power extraction is sufficient to prevent a safe autorotation. Now I'll show what happens when the clutch disengages. All of the things I've identified with the callouts, those components behind the clutch, have now stopped rotating, but the gears in front of the clutch continue to rotate. The clutch's ability to stop sending power to the high-speed, high-drag components prevents excessive parasite power from slowing down the rotor system, and this allows safe one-engine inoperative and autorotative flight. An important point here is that the takeoff pinion for the Interconnect drive system is in front of the clutch, so this means the Proprotor gearboxes and the Interconnect drive remain connected even after the clutch disengages. In the case shown on the screen, the left-hand engine has failed and the right-hand engine continues to provide power, not only to the right-hand prop rotors, but also across the wing drive shaft, through the tilt axis gearbox, then via the Pylon drive shaft and into the Proprotor gearbox. This satisfies the safety objective of removing the parasite power of a failed engine and also maintaining symmetric thrust on both prop rotors. I'll zoom in to show a closer view of the Proprotor gearbox, and I'll hide the engine for clarity. The aircraft on screen is in powered flight. And now it shows the left engine failed and the clutch disengaged. You can see the gears with the callouts have stopped rotating. Now that we've looked at that macro perspective, let's take a look at what's happening inside the clutch. In the video, I'm showing a split screen. This shows the left and right gearboxes in an orthographic view looking forward. Currently, the clutches are in their normal all-engine operating condition. The clutch works because of the geometry of the internal sprags. The sprags are longer in one axis than they are in the other, and this means they wedge in between the raceways when the clutch moves in the drive direction, but they have clearance and unwedge themselves when the clutch rotates opposite the drive direction. It's the friction in the system, aided by an energizer spring, that causes the sprags to wedge themselves in one direction, and then it's friction that causes them to unwedge when they turn the other direction. In powered flight, the outer race is driving and the inner race is driven, although that's design specific. I chose to make my design with outer race drive. That's what you see in the video now. The sprags are wedged between the outer and inner race, and this transmits the drive power. Now I'll change the video so the sprags on the left are in the unpowered overrunning position while the sprags on the right are in their normal powered position. The video now represents a one engine in operative condition with the right engine providing power. In unpowered flight, autorotative forces keep the prop rotors turning, but the engine starts to slow down. As soon as the engine slows down, the inner race becomes a driving component, but the inner race is unable to drive the outer race due to the geometry of the sprags. This is the overrunning position, and this disengages the failed engine and input gears from the drive system. In fact, I keep talking about engine failure, but it's not actually necessary for the engine to fail for the clutch to overrun. All that's needed is for the prop rotors to turn at a faster relative speed than the engine. It's not all that common, but it is possible in both helicopters and tilt rotors to go in and out of clutch engagement during aggressive maneuvering flight, even when the engines are operating. Now I'll change the video one more time to show a dual engine failure condition where the sprags on both sides are in the overrunning position. In a comment to my first tilt rotor video, a viewer asked me to discuss the hard clutch engagements that have been in the news lately. Generally speaking, clutch failures are extremely rare, but they're not a new type of failure, and they're not a failure that's unique to tiltrotor aircraft. In the video description, I linked to a TSB accident investigation report. This is from a Bell 206 helicopter accident. And I linked to it because it gives a very good description of what it means to have a hard clutch engagement failure. In the report, they say, the freewheel assembly did not engage as the throttle was rolled on during a power recovery autorotation. When the Sprag clutch suddenly engaged, the inertia built up in the power turbine gear train was resisted by the mass of the decelerating main rotor, resulting in the overstress failure of the mast. It's interesting that they refer to it as both a freewheeling assembly and a Sprag clutch in the same sentence. Probably should stick to consistent terminology. Despite that, it's still the most clear and succinct description of a hard clutch engagement failure that you're likely to find. In the video description, I also linked to a Sprag clutch failure mechanism guide. This is from a manufacturer's website, and it may be helpful if you're interested in understanding more about clutch failures. This discussion of clutch failures is an interesting commentary on humans and our machines. Sprag clutches are safe and proven technology. They have application far beyond helicopters and tilt rotors. It's fair to say that every day, almost every one of us trusts our lives to the hidden complexity of safety-critical technology. We usually think of this in terms of complex hardware and software, but simple mechanical systems like Sprag clutches can also be safety-critical. The fact that failures happen and from time to time have catastrophic outcomes doesn't mean that we have bad technology, bad operators, bad mechanics, or bad engineers. Rather, it means that nature is complex. It's complex beyond any notion that 100% safety assurance is ever possible. But still, we have to recognize that failure is always caused by the imperfection of humans, and it's always preventable. It's not enough that we design systems to be safe. We also have to seek out and acknowledge failures, ideally before they manifest as catastrophic failures. We have to relentlessly attack the root causes of those failures, and we must never demand perfection because it's never attainable. Instead, we need to acknowledge imperfection and seek continuous improvement as the real goal. Thank you for taking some time out of your day to learn with me about these interesting aircraft. I look forward to making more videos on this topic, and I'll see you on the next video.